Welcome to subsection 3.6.2 on the directional derivative. Definition 3.6.2, let u hat be a vector u1 through un be a unit vector. Let a, which is a1 through an, be a point, and let f of x1 through xn be a function. Then the directional derivative of f at a in the direction of u hat is d sub u hat of f at a1 through an is the limit as h goes to 0 of f of a1 plus h times u1, a2 plus h times u2, all the way up to an plus h times un, minus f of a1, a2, an, all divided by h, if this limit exists. So that is a familiar feeling limit. It is a derivative limit, but now we're making incremental changes in each of the variables, not just in one of them like we did for the partial derivative. So what is the interpretation of this directional derivative? To get a better handle on that, we're going to look at a function of two variables, f of x, y, at a point AB in the direction of a unit vector, u hat, very important that it's a unit vector, u1, u2. So the definition of the directional derivative in this case becomes the limit as h goes to 0 of f of a plus h times u1, b plus h times u2 minus f of ab over h. So like we did with partial derivatives, I'm going to put the point ab, I'm going to embed it in the xy plane. And I'm also going to embed the unit vector u hat. So there's our vector u hat embedded in the xy plane. And we're going to imagine that we have a surface, again, f of xy floating above. And the same thing that we did with partial derivatives, we imagined a plane and a curve of intersection, and we're going to do that here too. But our plane is not going to be parallel to the coordinate axes. Our plane, we're going to imagine that we're extending the direction of u hat, and our plane will be parallel to the z-axis and parallel to this direction of u hat. So we again are going to get a curve of intersection. We'll have the image of our point AB on that curve of intersection. And the directional derivative is going to give us the instantaneous rate of change of the function at the image point, so AB, f of AB, in the direction of the u hat vector. Now my u hat doesn't look quite straight here, so let's maybe fix that. The idea is that this is supposed to be perfectly parallel there. So there's our vector u hat. So d sub u hat of f at a1 through an represents the instantaneous rate of change of f at the point a1 through an in the direction of u hat. So if we relate this back to the partials that we had done before, the partials of f of x, y, well, the x-axis and the y-axis have direction. The x-axis has direction I hat, and the y-axis has direction j hat. So the partial derivative, f sub x at ab, could also be written as d sub I hat of f at ab, and the partial with respect to y could be written as d sub j hat of f of ab. In the next video, we will do a theorem which will give us a method for calculating the directional derivative other than taking a limit.